All right, so we're going to do a practice problem which has to do with orbital speed, energy, and period. And let's see. Yes. Here's the problem. A space transportation vehicle releases a 470 kilogram satellite. So our little m is going to be 470. While in an orbit at an altitude of 280 kilometers above the surface of Earth. Okay, so that's where it starts. A rocket engine on the satellite then boosts it into a geosynchronous orbit. How much energy must it provide? So it goes from there to geosynchronous. And we want to know the change in energy. Pardon me. All right. So let's talk about geosynchronous and geostationary for a moment. Geosynchronous, period of orbit, same as Earth, so 24 hours. Geostationary is probably what the question actually means, because most geosynchronous satellites end up being put into a geostationary orbit. Now it is just a geosynchronous orbit over the equator. And something placed in a geostationary orbit will appear to stay in the same place in the sky throughout an entire day. So if the Earth is orbiting at some speed and the satellite's orbiting at the same speed, they constantly turn so the satellite stays in the same place in the sky. So that would be geostationary. We don't really care. All we really need to know is that it is geosynchronous, which means we can use the period of the Earth, 24 hours, to figure out the radius that it must be put in. All right, what would this look like? Well, something a bit like this. You start with your Earth and your satellite, oopsies, in orbit around it, headed in some direction, making a circle. And at this point it is at an altitude of h, and we've got the radius of Earth on the other side. But it's going to be boosted, and it's going to be put up into an orbit eventually with a different speed, where it is traveling around in a different circle. And there we have some particular distance between their centers r. So we've got a few different things we have to find here. We have to find that radius r, which we'll do from the period. We have to figure out what the energy looks like for an orbit. So we're going to do both of those in just a moment here. Okay. Sorry, got quite a cough just at the moment. It's probably allergies the way I work though, so no worries there. All right, let's talk about period. So period is going to be the distance divided by the rate, which is going to be 2 pi r divided by rate. The rate, if we want to find the rate, we'll have to use Fg is equal to MAC to figure it out. So that will give us minus g mass of Earth, mass of satellite over r squared is minus mass of satellite, speed of satellite squared over r. Okay, so that means v is the square root of g mass of Earth over r. All right, we'll take that over. We're also going to want that for our energy side of things, so it's good that we found it. All right. Let's see here. So the period will be equal to 2 pi r over the square root of g mass of Earth over r. And that means we can rewrite this as 2 pi over the square root of g mass Earth, radius of Earth, or sorry, radius of the orbit to the 3/2 power. We're trying to find r here, so we're going to rearrange to isolate the r. So r to the 3 halves will be equal to the period times the square root of g times mass of Earth all over 2 pi. And then we'll have to, let's see, square everything on the other side and take the cube root. So it will look like cube root of period squared g mass of Earth, because remember we're squaring everything. That's what the 2 on the bottom is requiring us to do. We're having to get rid of a square root. So this would tell us that geosynchronous radius. Just for curiosity's sake, I am going to throw that in there. The period must be in seconds. Why? Well, because g, big G, is actually in seconds. It contains a Newton, and Newton contains seconds squared. So we're going to have 3,600 times 24. That gives us the period in seconds, 86,400. Square that, multiply by big G, 6.674 times 10 to the minus 11, times mass of Earth, 5.97 times 10 to the 24. Then we'll have to divide by 4 and pi squared and take the cube root. And it gives us 4.22 times 10 to the 7th meters. Remember, the radius of the Earth is around 6 times 10 to the 6th meters. So this isn't quite 10 Earth radii out, but it's a long way out there. Now, I'm actually not going to use this, because I'm going to take that r equation and I'm going to use it directly, and it will look ugly, I admit, but all right, energy is 1/2 mv squared minus g mass Earth mass satellite over r. So our energy initial can be rewritten very simply, because the v is just going to be this v for a circular orbit we found. So 1/2 m gme over r minus gme m over r will be minus g mass of Earth mass of satellite over, and where we're starting is re plus h. Let's see, no reason we can't do energy final the same way, so it's going to follow generally the same equation, but it's going to be minus g mass Earth mass satellite over the r we just found. All right, and the change in energy required to make orbit, is just going to be the change in these two, so energy final minus energy initial. The rocket motor is providing energy, so there is a change in energy here. It's not change in energy equals 0. All right, so I don't know, let me see here. I suppose we can factor out g mass of Earth mass satellite. That'll leave behind 1 over the r I just found minus 1 over the re plus h. All right, I'm going to admit I'm going to do this all on my calculator right now. So negative 6.674 times 10 to the minus 11 times 5.97 times 10 to the 24 times mass of our satellite was 470. Okay, so I've got the minus GMEM part times parentheses 1 over, I've got the answer I just found for the radius saved, so I'm using it, minus 1 divided by 6.37 times 10 to the 6 radius of Earth plus the altitude. Now notice the altitude was given in kilometers. I need to convert that to meters, so I'll take 280 times 10 to the 3 there. And I'm getting a change in energy of 2.37 times 10 to the 10 joules. Okay. Let me see, which one was this? 11? That's interesting. pausing video for a moment. All right, I figured out what's going on. This difference. There should have been a 2 over 2 here, so there is a 2 on the bottom. So basically my answer from before is off by a factor of 2. Hey, we all make mistakes sooner or later. I do like leaving this kind of mistake in the video, by the way, so if you're looking for mistakes in videos to report to me, this kind of thing is the sort of thing where it's modeling how do you recover from a problem. So what happened? I checked the answer that I have on the sheet, which will be included inside of the file itself. So when you are looking at the lecture notes, you should see the answer that you're supposed to get in here. And I'm going, wait, that's not what I got before. So what's going on? So I started going back through, and as I was checking other things, the first thing I checked is that the radius that I found geosynchronous was right. And almost as soon as I did that, I found the missing 2. So as soon as I found that, I knew what my problem was, and in theory, 2.37 times 10 to the 10 divided by 2 should be 1.18. Yep. So we get 1.18 times 10 to the 10th joules. Okay. Pardon the cough, goodness. That's pretty much it for this one. I need to remember to make sure the answers are all placed in the different sections. I'm going to stop the video here, and good luck trying it for yourself. You absolutely should try these problems for yourself when you get the chance to make sure that you can reproduce it on your own without following along. All right, so see you in the next video.